Hello everybody, this is my lecture for ME3011 Thermodynamics, Wednesday, March 18. Today I will go over the previous lecture. Also, we will solve two examples and then we'll discuss pipe and ducts. So, as a short summary, we discussed the general equation for energy balance of open systems. So for the open systems, you can write Q net minus W net equals to the sigma m dot out times enthalpy, kinetic energy, and potential energy minus the sigma m dot h potential kinetic energy, potential energy, and enthalpy. So for the specific case, if there is one inlet and one outlet, you can simplify this equation into this format. Keep in your mind that you can use this equation, a special case when there is one inlet and one outlet for most engineering equipment, for all turbines, compressors, um, normally heat exchangers, throttling valves and diffusers, nozzles, all these equipments work under the steady state conditions, and normally there is one inlet and one exit. Also you can write this equation based on the unit mass. If you don't have the m dot, you can just divide both sides by the m dot. And then if you assume that the kinetic energy and potential energies are negligible, we already discussed it in the class, so you can simplify the first thermodynamic law for open systems and a steady state condition into this equation. Okay, now also we discussed throttling valve. If you remember, we simplified the first thermodynamic law for throttling valve into this format, meaning that the enthalpy is constant in throttling valve. Enthalpy in the exit equals to the enthalpy in the inlet. For the heat exchangers, if you remember, we can set two different equations. We can set two different equations for mass conservation and two equations for energy conservation. So you can set one mass conservation equation for hot fluid and one mass conservation equation for cold fluid. So you can write m dot in for the cold fluid equals to the m dot out for the cold fluid, and m dot in for the hot fluid equals to the m dot out for the hot fluid. Also, you can set two energy conservation equations for the hot and cold fluid. In the previous lecture, we proved that you can set this equation for the cold fluid and then this equation for the hot fluid. And eventually, keep in your mind that this is a fundamental equation in design of each and every heat exchanger. You can write Q in for the cold fluid equals the Q out of hot fluid, or this equation. So for the enthalpy change of fluid, you learn in chapter 4, there are 4 different methods to calculate the enthalpy changes from the tables, using the integral format, using the CP average or CP constant at 300 Kelvin. So energy and mass conservation equation for mixing chambers is a little bit different from turbine, compressor, diffusers, heat exchangers, nozzles, and the previous, equipment that you learn in this course. For the mixing chambers, normally there is more than one inlet. And so you need to write the general mass conservation equation. Sigma m dot in for a steady state condition equals to sigma m dot out. And for the energy conservation, you need to use the general equation. You need to just set it based on the sigma m dot out and sigma m dot in. Now, let's solve, some examples from this part. Please open the PDF file that I share with you on the Blackboard. Please open file 578 ME3011, this PDF file. This is a question about the heat exchanger design. Here you can see a double pipe heat exchanger, and the hot fluid is a kind of oil, we have the m dot and the th in is 150, and then the tho is 40 centigrade. Cold fluid is water with the mass flow rate at 1.5 kilogram per second. The T inlet is 22 degrees centigrade, and the T exit, the T cold in the exit is unknown. So, first of all, guys, please spend 2 minutes. Pause this video. Please spend 2 minutes and then complete this table. So I already add some information, but please go over, the information and then just complete this, table for 2 minutes. Okay, guys. Now, so after you spend 2 minutes, hopefully you just complete this, table. Keep in your mind that you have the CP. When you have the CP, it means that you can assume that this specific heat is constant. So this is key point to solve this problem. Now let's move forward to the second step. So guys, here I list all equations that can be used to design a heat exchanger. Actually, there are three equations, correct? You can also set two equations for the mass balance. I just set equations for the energy balance. Equation one is the heat balance equation or energy balance equation, sorry, for the cold fluid. And so I told you, because Cp is constant, you can rewrite this equation, the delta H, based on the Cp, correct? So equation two is the energy equation for the hot fluid. Again, because the Cp is constant, I rewrite it into this format. And the third one is the energy balance between the hot and cold fluid. So you asked to find the Q dot, the heat rate. Just spend 2 minutes, work on these three equations. Which one do you think is useful to find the rate of heat transfer? Just spend 2 minutes, and then based on the available information, which one do you think is the best one to solve actually Q dot? Okay, guys, let's start from the first equation. Here you can see, those equations. So let's start from the first one. If you want to calculate the Q dot by using the first one, you need to have the M dot. M dot for the cold fluid is known. Cp for the cold fluid is known. Tc in the exit is unknown. So you are unable to use the first equation to find the Q dot, because the exit temperature of cold fluid is unknown. Let's check the second one. If you want to find heat transfer rate by using the second one, m dot h is known. Heat capacity of hot fluid is known. TH1 and TH2 are known. So you can use this equation because everything is known. So use this equation to find the Q dot. Everything is known. You can spend 2 minutes, pause this video to calculate the Q dot. Okay, if you just substitute the unknown parameter here, you can simply find the Q dot. Keep in your mind that because the Cp is in kilojoule, the unit of heat transfer rate will be in kilowatt. Okay, the second step, you are asked to find the exit temperature of water. To find the exit temperature of water, let's go here. Okay, so again, please check these three equations here. Which one do you think is the best one to find the exit temperature of cold fluid? Look, guys, so the exit temperature of cold fluid is, okay, let's spend 2 minutes, guys, and then we can discuss it, which one is the best one. So let's spend 2 minutes. Which one do you prefer to pick to solve, the second part of this problem? Okay, guys, so if you check, the first equation, this is the only equation that includes the unknown parameters. I mean, the exit temperature of cold fluid. So you must use this equation, correct? But keep in your mind that you already determined the Q dot for the hot fluid, correct? And from the third equation, you know that this Q dot out equals the Q dot in of cold fluid. So you have the Q dot. You can substitute here to calculate the exit temperature of cold fluid. Yeah, here is calculation for the second part. So you can simply find the exit temperature of cold fluid. Now let's solve another one. This question is for actual mixing chamber. We have two streams. The first one is probably subcool liquid. You have the temperature for the first one, and the second one is superheated vapor, I think is to be, yeah, the second one, this stream is the superheated. So here you have the temperature and pressure, so you can find the state of this water. This is probably subcooled, and then this is the superheated vapor. So we mix these two streams to just make saturated liquid at 1000 kilopascal. Pressure is constant in all these three streams and equals to the 1000 kilopascal. So you are asked to find the ratio of m dot 1, this one, over m dot 2. Now, to solve this problem, let's go. Please open PDF file 172. Oh, sorry, it's not the right one. Please open file 572 available on the Blackboard. So look guys, to design this actually kind of mixing chamber, we normally assume that the Q dot net to the surrounding is 0. There is no heat exchange between mixing chamber and surrounding. So if you select the whole mixing chamber as a control volume, then you can assume that the Q dot net is 0. Okay, please spend 2 minutes, guys. I just add some information to this table. Please spend 2 minutes and then complete this table. Keep in your mind that here you have two inlet 1, inlet 2, and then one exit. So spend 2 minutes and then add all available information to this table, please. Okay, now to solve this problem in a second step, I listed all equations for mixing chambers. So we have mass balance and energy balance. So for the mass balance, you can write sigma m dot in equals to sigma m dot out. So please spend 5 minutes and then simplify these two equations for this specific case. Keep in your mind that there is no W, and then probably you can assume that the changes in kinetic and potential energies are negligible. 5 minutes and then simplify these two equations. Okay guys, so I selected the whole mixing chamber as a control volume. So let's write the mass balance. So we can write sigma m dot in equals to sigma m dot out. There are two inlet, m dot 1 and m dot 2, and there's just one exit, m dot 3. So for the energy balance, this is the energy balance equation. So we assume that the Q dot net is 0 because I select the whole mixing chamber as a control volume. There is no W shaft, no electrical work, so you can cancel this one. And then you can assume that the kinetic and potential energy changes are negligible. So if you just add this information, This will be the energy balance equation. M dot 1 H1 plus M dot 2 H2 equals to M dot 3 H3. Now, we are looking for the ratio of M dot 1 to M dot 2. We can combine, as a next step, we can combine the energy balance equation and mass balance equation. How we can substitute for the M dot 3 from the mass balance equation. So if we combine these two equations, then this will be, the final equation. And now we are looking for the M dot 1 over M dot 2. You can simply divide both sides by the M dot 1. If you divide both sides by the M dot 1, this is the equation, correct? So this is the unknown parameter, So to find the M dot 1 over M dot 2, what you need to do, you need to find H1, H2, and H3. So for the H2, H1, you have the temperature and pressure. Temperature is 50 degrees centigrade and pressure is 1000 kilopascal. This is probably compressed liquid. So you can check, the table, this saturated table for water for this one. This one, you know that this is the superheated. You have the temperature, pressure, check the superheated table to find the H2. And this one is saturated liquid. So you need to find this, to check the saturated table to find H3. Okay, please spend 5 minutes to find H1, H2, and H3. And then we can solve the, remaining part. Okay. So these are the H1, H2, and H3. If you substitute into this equation that we already draw, we can find the ratio of M dot 1 over M dot 2, which is 3.73. Okay, again, guys, look what we did. We play with the mass balance and energy balance, and then we just, solve the problem by combining these two problems. These two equations, sorry. Now, so this is the last part of this, steady state equipment. So the last one is pipe and duct. We already discussed pipe and duct in chapter 2. Here we just go over, more detail. So normally pipe and ducts are used to transfer fluids from one point to the other one. For the Q, normally we can have different type of works. For in pipe we may have W shaft, we may have electrical work. For the Q dot in or out, I recommend you to consider this, Q dot in and Q dot out. In most cases, you may have Q dot in or Q dot out. However, you can cancel Q dot out or Q dot in if you have a good, insulation around this, pipe. But keep in your mind that for the pipe and ducts, normally you can assume that the delta kinetic energy and delta potential energy is negligible. They are insignificant. And then you can start from the first thermodynamic law as from the energy balance equation for a steady state equipment, and then you can just drive equation for each and every case. So what's the difference between pipe and duct? Normally pipe has the circular cross-sectional area, and duct they have non-circular cross-sectional area. So for the flow through pipe, you can assume that the M dot in equals to the M dot out. And I have a example here. This is a very simple one. We already solved several examples for the pipe and ducts. Here you have a duct, and then we have the some information, the inlet pressure and temperatures, and also the volumetric flow rate are known. And so also we know that the heat transfer rate to the surrounding is 2 BTU per second, and you're asked to find the velocity of air. To find the velocity, guys, you have the volumetric flow rate, and then you can use the relationship between volumetric flow rate and velocity. You can write the volumetric flow rate equals to area, cross-sectional area, times velocity. So the diameter is known. You have the diameter, and yeah, the diameter is 10 inch, and then you just need to find the cross-sectional area. So by having the cross-sectional area, you can simply find the, velocity. So volumetric flow rate is velocity times area, and then from here you can find the volumetric flow rate. So then for the second part, you are asked to find the temperature in the exit. So to find the temperature, folks, you need to set the energy balance equation. So before that, it's a good idea if you calculate the m dot. You have the volumetric flow rate. It's a good idea if you calculate the m dot. So to calculate the m dot, you have the volumetric flow rate. Then if you found the specific volume in the inlet, then you are able to find the m dot. So, and the specific volume can be found by using the ideal gas equation of state. Now, what you need to do, you need to set the energy balance equation to find the exit temperature. Spend 2 minutes and then please set the energy balance equation for this, duct. Okay, this is the energy balance equation for the steady state equipment with one inlet and one exit. So Q net is Q in minus Q out. Here we have Q in, Q out is 0. For the W, I think we don't have any information for the W. Let's check it one more time. Yeah, we have nothing for the W, so we can assume that the W is 0. And then enthalpy in the inlet and exit, you need to keep the enthalpy. Diameter is constant. You can cancel the velocity changes and then also the potential changes. So if you simplify this energy balance equation, and then if you use the average, CP for this, problem, you can just write it based on the average specific heat. So Q dot in is known. You calculate M dot in the previous part. So what you need to do, you need to find the CP, correct? To find the T2, T2 is unknown, you have the T1. Now, the question is that what is the best value for the CP average? If you remember, to find the CP average, we need to have the T1, T2, and then we need to find the T average, and then the CP is determined at T average. But the point is that the T2 is unknown. The exit temperature is unknown. So in this case, folks, let's look at the inlet temperature. The inlet temperature is 50. Correct? And we are adding 2 BTU per second, heat. So what we can do, we can assume that the exit temperature, for example, is something around, let's say, 100 Fahrenheit or 80 Fahrenheit, correct? And then if you remember from chapter 4, for the, a small interval of temperature, difference, you can assume that, the CP is constant. Just check, the reference table for the CP for the air, and then compare, for example, the CP at, let's say, 300 and, 350. You can see that, the changes, the change in, CP is really negligible. Now, so what I'm going to do, I'm going to use the table A2. Correct. The table A2 is ideal gas specific heats of some gases at 80 Fahrenheit. Correct. So I'm going to use, this CP at 80, Fahrenheit. And then this is based on this table, the CP is 0.24 BT per pound mass Fahrenheit. Let's use this CP to find the exit temperature. If you use this CP here to find the exit temperature is 64. So exit temperature is 64. If you calculate this average temperature, the average temperature is, the inlet is 50, the exit is 64, so the average temperature is 57. And I use this specific heat at 80 Fahrenheit. 57 or almost 60 to 80, there is just 20 Fahrenheit, difference between, my assumption and the exact value for the CP. And this is really negligible. Don't spend your time, don't waste your time to find the exact value for the CP. So this is really good assumption by using that table for this case. Okay, guys. So this is the last slide. Please go over this material, and then if you have any question, please send me an email. Have a great day.